Hi everyone, this is week 3 of NPTEL course Introduction to Algebraic Geometry and Commutative Algebra. This is a course under Professor Dilip Patil, and we will be doing this assignment for week 3, and the topic of today is algebras, that is algebra over a ring. So before going into the preliminaries, let us go through before going through the uh, exercises and problems, let us go through the preliminaries. Let A be a commutative ring, and a more often used property is so called the universal property of the polynomial algebra over A. For every commutative A algebra B and an indexed set I, the map, that is the all the A algebra maps from the polynomial ring AXI to B. This the algebra generated by this to BI. B to the power I means B times B times B times up to the cardinality of up I times. The map should be something like this. A goes to f of xi. It is clear from this, right? And this is bijective. Now, for each I tuple x of xi, uh, the substitution A algebra homomorphism, uh, that you are gonna substitute this A capital Xi by small xi. This maps should be something like this, and this is an A algebra homomorphism that you have to check yourself. And again, these are some preliminaries given from your note that you can check for yourself. So I'll be skipping them because there is no point reading these things, since you can read this preliminary by yourself. Now we'll be going to our problem number 1, that is 3.3 from the um, assignment. Let A be an integral domain, and so our first problem will be something like this. Let A be an element from the polynomial ring generated by x over A, and let n be a integer. uh, so what is VAF? VAF is it will be here. Let me check. One second. So they have defined VBGJ something like this. Uh, A should be these elements from BI such that Gj is 0 for all small j belongs to capital J. So Gj are the polynomials. So what they are trying to say is that it is the zero set uh, over b uh, of gj. That means if so here VAF, let me write, VAF should be f is your coming from single uh, variable, so should be x belongs to a, such that your f of x equals to 0. That is the zero set of the zero set of the polynomial. So if the cardinality of this set is greater than n, then either f is 0 or degree of f is greater than n. So kind of this is fundamental theorem of algebra, right? Where you can recall the fundamental theorem of algebra. One second. Okay, so let us prove the contrapositive first. If f not equals to 0 and degree of f is greater than equals to n, then this cardinality of VF is less than equals to n. So we will be proving this, that if f is not equals to 0 and degree of f less than equals to n, then this will be true. Then its contra negative is this, that this is what is given here. So anyway, so let us assume these two conditions. Suppose f is not 0 and degree of f is less than equals to n, which is d. We will show that f has at most d roots in a, which implies v of af, cardinality of v of af is less than d and less than equals to n. The proof proceeds by induction on the degree of f. So if d equals to 0, then f is a non-zero constant polynomial. So f of a not equals to 0 for all small a belongs to capital A. Thus v of af is phi, and the cardinality of this set should be 0. You know the empty set has cardinality 0, and assume the result holds for all non-zero polynomials of degree less than d, that is less than equals to d minus 1, where d is greater than equals to 1, and let f belongs to x with degree of f equals to d. Now let us consider the case 1, that if v of af equals to phi, then v of af, cardinality of v of af equals to 0, which is less than equals to d, and we are done. And the case 2 says that suppose v of af is not equals to phi. One second. So suppose v of f not equals to phi, and let alpha belongs to v of f be a root of f, that is f of alpha equals to 0. By the factor theorem, which holds for integral domains, since alpha is a root of f, we can write that f of x equals to x minus alpha into g of x, and first of g of x belongs to x. Now, since A is an integral domain, X is also an integral domain, right? And therefore, degree of f equals to degree of x minus alpha into g of x, and which implies that degree of x minus alpha plus degree of g of x. And since degree of x minus alpha is 1, we have that degree of f equals to um, 1 plus degree of gx. This implies degree of gx is d minus 1, which is clearly strictly less than d. And since we are implying induction theorem, so now if gx equals to 0, then fx equals to 0, contradicting our assumption that f not equals to 0, thus gx not cannot be 0. Now we claim that that v of f is contained in this uh, alpha union v of a of g. Now proof of this claim should now if you take beta from v of f, then f of beta equals to 0, which means that this expression is true, that is b minus alpha into g of beta is 0. And since a is an integral domain and has no zero divisors, so either this entity is 0 or like this entity is 0. This means either b equals to alpha, beta equals to alpha, or beta belongs to v of ag, and thus beta belongs to this set. And by the induction hypothesis, since g is not equals to 0 and degree of g is d minus 1, we have that this condition is true. Therefore if you check cardinalities, you will see that v of f is less than equals to d. Cardinality of v of f is less than equals to d. So this completes the induction, and therefore we have shown that if f not equals to 0 and degree of f is less than equals to n, then this is true. And the contrapositive statement is this, which was given in the problem itself. That is this. Now, a simple corollary to this problem can be like this, that a non-zero polynomial f of x of degree d has at most d roots in a, which is again the like weakened version of fundamental theorem algebra, but for the arbitrary ring case. We are weakening the condition on the field, and we are saying that it can be ring itself. Now, uh, so there are this one also, that now we'll be moving to the next problem, but you can clearly look into this following this problem, right? Following this problem given here, that this is exactly saying this, that the zero set of f has at most n elements, that is I mean, if the d is replaced by n, then it should be at most n roots here. Okay, so now we move to the next problem, that is if a is infinite, a is a ring, and f and g are two polynomials from this polynomial ring AXI, which is generated over this variables xi's, and if this a power I, that is the I times like the multiples of a minus the zero set v of f is contained in v of a of g, then g is 0, which is which again we will prove this. And so there are two cases. Suppose I is finite, and there is another case, that is suppose I is infinite. So we will only prove the I finite case, and we'll leave the I infinite case as an exercise. So now we will attempt to prove this. We are given that f not equals to 0, and this subtraction is contained in v of a g. The condition a to the power I minus b of a of f is contained in v of a of g means for all tuples from a to the power I, if f of this tuple is non-zero, then g of this tuple is 0. And equivalently, you can say that for all tuples from a to the power I, either f of this tuple is 0 or g of this tuple is 0. Now we'll prove this finite case, and you can check that this infinite case also follows by a similar technique. We proceed by induction on the number of variables m. So induction is a great tool to follow always. So we'll first check the base case, that is m equals to 1. We have f and g coming from a of x1 with f not equals to 0. The condition states that for all small a belongs to capital A, if f of a not equals to 0, then g of a equals to 0. And suppose for contradiction that g not equals to 0, and let degree of g equals to d. By part A, g has at most d roots in A, and therefore the zero set of g has cardinality less than equals to d. And since f not equals to 0 and A is an integral domain, we know that the complement a minus b of a is contained in VAG, and therefore we have that this condition A is the union of v of AF, union of a minus v of AF, which is again contained in v of AF union v of G, because this is contained in this. And since f not equals to 0, v of AF is not equals to A, and this follows from this condition, which you can read by yourself. And actually since f not equals to 0, and let a degree of f equals to n, so by part A we can see that v of A its cardinality is less than equals to n. Now since a minus v of A of f is contained in v of A of G, we have this condition that cardinality of A should be equals to v of A of f union A minus v of A of f. And since this is a disjoint union, their cardinality should be uh, distributed additively. And since A minus v of A of f is contained in v of A of G, and v of A of G has cardinality less than equals to d, assuming that g not equals to 0, we get this A minus VF is less than equals to VAG is less than equals to D, and this gives us this, that cardinality of A should be finite, that is n plus D. But A is infinite, right? Therefore this is a contradiction, so G must be 0. So we have proved our base case. So you see that the base case is quite uh, non-trivial. But anyway, uh, now we shall assume the inductive step, that is, the assume the result holds for polynomials in m minus 1 variables where m is greater than equals to 2, and consider f and g are elements from a of x1 to xm with f not equals to 0, and a of m minus b of a of f is contained in v of a of g. Write f and g as polynomials in xm with coefficients in a of x1 to xm minus 1, and f of x1 to xm can be written like this: summation of fk, which is a polynomial from x1 to xm minus 1, and x to the power k m, xm to the power k, and g of x1 to xm, which is a which can be rewritten as this, that summation of gj of x1 to xm minus 1 and xm to the power j, where fk and gj are elements from a of x1 to xm minus 1. Since f not equals to 0, there exists some small case such that f of k not equals to 0, and for any fixed tuple a1 to a minus 1, we can define this polynomial, that is small f of xm should be something like this, that is x1 to x m minus 1 is replaced by a1 to a m minus 1, and for g you can again check this is replaced. Now if small f is not equals to 0, then for all small m belongs to am belongs to a, if f of am not equals to 0, then g of am is 0 by our assumption on f and g, right? By the base case, this implies g of g equals to 0. This implies that capital G of a1 to a m minus 1 comma xm equals to 0 as a polynomial in capital xm. This means that capital G small j in bracket small a1 to small a m minus 1 equals to 0 for all j from 0 to d. Now, since A is infinite, there exists infinitely many choices of a1 to a minus 1 for which f not equals to 0. And by the induction hypothesis applied to each gj, since each gj vanishes on an infinite subset of a to the power m minus 1, that excludes the zero set of this some non-zero polynomial, we can conclude that gj equals to 0. Therefore, g equals to 0. Now, which I said earlier, that since I is infinite, a similar argument it can be used. The fact that non-zero polynomial only it depends only on finitely many variables. Therefore, uh, from infinite case to you can come down to finite case and do this by yourself. Now we'll be approaching this problem, that is identity theorem for polynomials, and you can take some time to read the statement, that is let small a be a polynomial from AXI with variables capital XI and small I coming from capital I over an integral domain A. If there are subsets Ni content in A with cardinality of Ni is greater than degree of Xi over F, that is the highest power of Xi in F for all small I belongs to capital I, then n is the product of this ni which is not contained in v of a of f, that is there exists an element small x belonging to capital N with f of x not equals to 0. So you can again read it by yourself to understand the statement, that is saying that cardinality of ni is greater than a degree of xi of f, and if every each of ni is like this and n is the product of them, then you can see that this n cannot be uh, contained in the zero set of f. And in particular, if a is an infinite integral domain, then the polynomial function a to the power I to a, that is f of uh, I mean, you can just replace the value of the variables by the tuples from a to the power I. Then the polynomial function this defined by a non-zero polynomial f is not the zero function. That is, if f is a non-zero polynomial, then it has a non-trivial solution. This is called the identity theorem for polynomials. Yeah. Okay. Now we prove the main statement of the by induction on the number of variables on which f depends non-trivially. Since f is a polynomial, it depends on only finitely many variables. Thus, we may assume without loss of generality that I is finite. Say I equals to from small 1 to n, and we proceed by induction on small n. The base case is that if n equals to 1, that is f belongs to capital AX1, be a non-zero polynomial with f not equals to 0. Let d equals to degree of x1 over f, and suppose n1 is less than is contained in A with cardinality of n1 greater than d. And by the problem we have done above, we can see that since f not equals to 0 and degree of f equals to d, the polynomial has at most d roots in A. Therefore, v of cardinality of v of af should be less than equals to d, which should be strictly less than cardinality of n1. And since cardinality of v of f is strictly less than n1, we have n1 not contained in v of a of f. Thus, there exists small n x1 belongs to n1 such that f x1 not equals to 0. Now, assume the result holds for all non-zero polynomials in n minus 1 variables over any integral domain where n is greater than equals to 2. Let small f belongs to a of x1 to xn be a non-zero polynomial, and write f as a polynomial in xn with coefficients in a x1 to xn minus 1. And since f of x1 to xn equals to summation of fk of x1 to xn minus 1 uh, with the product of xn to the power k, where fk belongs to ax1 to xn minus 1 for k equals to 0, 1 to m, and fm not equals to 0. And note that degree of degree of xn in f is m. And since f not equals to 0, we have fm not equals to 0, and moreover for each small I belongs to this set, degree of xi of fm is less than equals to degree of xi of f. This is clear, right? Because fm is coming from this polynomial. Now let n1 to nn is contained in uh, capital A with ni with cardinality of ni is strictly greater than degree of xi of f for all I from 1 to n. Now step 1, what we will do is that apply the induction hypothesis to fm. Since fm belongs to the polynomial ring over A generated by x1 to xn minus 1 is non-zero, and cardinality of ni is greater than degree of xi over f, which is greater than equals to degree of xi over fm for all I equals to 1 to n minus 1. By induction hypothesis applied to fm, which is a polynomial in n minus 1 variables, there exists a tuple from n1 to n minus 1 such that this is not equals to 0, and this follows from the induction hypothesis. And consider the univariate polynomial obtained by evaluating at a1 to n minus 1, which you can define by g of xn equals to f of a1 to an minus 1 of xn equals to summation of fk of a1 to n minus 1 x to the power k xn to the power k belongs to a of xn. And since fm of a1 to n minus 1 is non-zero and is an integral domain, we have g of xn not equals to 0 in a of xn. Moreover, degree of xn of g equals to m, and degree of xn of f equals to m also. So now if we apply the base case to g, since g is non-zero with degree of xn of g equals to m, and n of n suffix small n, its cardinality is greater than degree of xn over f, U is equals to m by the base case applied to the univariate polynomial g, there exists small n from n suffix small n such that g of n is non-zero, and therefore we have found that small a1 to small n is contained in capital N such that f is non-zero, and therefore capital N is not contained in V of A of f. Now we prove the particular case. Suppose A is an infinite integral domain, and f is contained in AXI, which is a non-zero polynomial, and we need to show that the polynomial function e to the power I to a by x going to fx is not the zero function. Now, since f is a polynomial, it depends on only finitely many variables. Without loss of generality, assume that f is contained in a of x1 to xn for some finite n, and for each I from 1 to n, let di be the degree of xi over f. Now, since a is infinite, we can choose subsets ni of a with ni, cardinality of ni, equals to di plus 1, which is greater than di, and which is equals to d of degree of xi of f. Simply, if we simply take any di plus 1 distinct elements from a, and by the main result proven above, there exists a1 to an which is an element of n1 times dot 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 up to nn, which is contained in an and which is contained in ai, such that f is not equals to 0. Therefore, the polynomial function defined by f is not the zero function, right? Now, we come to our next problem, but you can take some time to read this, and we'll start solving this after 2 minutes. Okay, so let us start solving this. Let small p be a prime number and let a be a finite field of characteristic p, which is greater than 0. And then we have to prove that cardinality of this field uh, equals to uh, p to the power n for some uh, small n belongs to this integer set of integers. Now, since small f has characteristic p, where p is prime, the prime field of f is isomorphic to fp, right? Which is z of pz. Uh, let small k denotes the prime field of f, that is this. And since f is a finite field containing k, we can view capital F as a vector space over small k, right? And since f is finite, it must be finite dimensional vector k vector space, right? And let n be the dimension of f over k, and by the hint, uh, I mean, since f is finite dimensional vector space over fp, it is clear that cardinality of small f is cardinality of capital F is cardinality of fp to the power n, which is p to the power n. And this follows because this basis thing which you already know, so I will skip this argument. But it is clear that the f should be written as something like this, right? Sorry, it should be something like this: f of p dxm up to f of p, and this is up to n times, so therefore the cardinality should be p to the power n, right? Okay, now we focus into our next problem, that is let q equals to p to the power n, and small n belongs to capital N, and n is greater than equals to 1. There exists a finite field extension uh, L over fp such that the polynomial x to the power q minus x splits into linear factors in Lx. Now we'll construct such a field L as a splitting field. Consider the polynomial small f of x equals to x to the power q minus x, where q equals to p to the power n. Let L be a splitting field of fx over fp, and by definition, capital L is the smallest field extension of fp in which small fx factors completely into linear factors. Now we need to show that L is indeed a finite extension and that x to the power q minus x splits into linear factors in Lx. Now show that the derivative of fx shows it is separable. And we should learn what is a formal derivative, that is f prime f dash x is q of x to the power q minus 1 minus 1, and which is p to the power n x to the power q minus 1 minus 1. And since pn congruent to 0 in mod p in fp, we have a prime x equals to minus 1, which is not equals to 0. Therefore, GCD of f of x and a prime x equals to 1, which means fx is separable. That is, it has no repeated roots. Now we have to show that the set of roots forms a subfield. Let capital K is the set of all small a of L such that a of q equals to a to the power q equals to a, and That means capital K is the set of all roots of x to the power q minus x in L, and we claim that K is a subfield of L. Now 0 and 1 belongs to K, right? Because 0 to the power q is 0 and 1 to the power q is 1. If now we check that if A and B belongs to capital K, then A plus B to the power q equals to A to the power q plus B to the power q, right? Because all the other terms would have something q times something, and since we are taking characteristic p and p divides q, so those terms are all 0, right? So therefore only these two terms remain, so non-zero. And since we already know that A to the power k is A and B to the power q is B, therefore we have this, that A plus B to the power q is A plus B, and so on, and so A plus B belongs to capital K. Now if small a belongs to capital K and small a is not equals to 0, then A inverse of q equals to A to the power q minus 1 equals to A inverse. So A inverse belongs to capital K, and if small b belongs to capital K, then small a b to the power q equals to A to the power q and B to the power q equals to AB, and so small a b belongs to capital K. Therefore K is a subfield of L containing all roots of x to the power q minus x. Step 3, that is, we have to show that since fx is separable of degree q, it has exactly q distinct roots in capital L. Since these roots form the field K, we have cardinality of K equals to q, which equals to p to the power n. Now since K contains all roots of x to the power q minus x, and L is the splitting field of this polynomial over Fp, we have L equals to K. And therefore x to the power q minus x splits completely into linear factors in Lx, which you can see here. And our aim was to show that uh, huh, the polynomial x to the power q minus x splits into linear factors, and we have shown that uh, this. So we are done. Now we'll start approaching the question sheet, and you can read it by yourself for 2-3 minutes, then we'll again start. Okay, so let us focus on the question C, that is, let L be a field of characteristic P greater than 0 and Q equals to P to the power n, and suppose that the polynomial x to the power q minus x uh, splits into linear factors in Lx, then the zero set of this polynomial is a subfield of L with this cardinality of zero set equals to Q. That being said, that let us define the K as the zero set of x to the power q minus x over L, that is elements of L which satisfy this equation, this. Now we have to show that K is a subfield of L, but this is clear again with this data that we have again done earlier, so we are skipping this. That is 0 belongs to K, since 0 to the power q equals to 0. 1 belongs to K, and since 1 to the power q equals to 1, if a of a comma b belongs to a K, then again a minus b to the power q belongs to uh, a minus b to the power q equals to a to the power q minus b to the power q, which equals to a minus b, and therefore a minus b belongs to K. And if a belongs to K and a not equals to 0, then a to the power q minus 1 equals to 1, and thus a inverse belongs to K. And if AB belongs to K, then AB to the power q equals to a to the power q, b to the power q equals to AB, and so AB belongs to K. Therefore, K is a subfield of L. Now, we have to show that cardinality of K equals to Q. Since x to the power q minus x splits into linear factors in Lx, and L is a field by the problem we have done above, that x to the power q minus x of degree q has at most q roots in L, but if x to the power q minus x splits completely into linear factors, it must have exactly q roots. Since the polynomial is separable, these are the q distinct roots. Therefore, the cardinality of K equals to Q. Now, we focus into our next problem, the question D, which says that let K equals to P to the power n, and let small n belongs to capital N. There exists a unique field up to isomorphism with Q elements. That means for any prime power, we have a unique field up to isomorphism with that cardinality. Now we will first show the existence, that is by part B, that is this. There exists a finite field extension L over P such that the polynomial splits into linear factors over L. So yeah, and by part C, the set of roots of K is a subfield of L with exact cardinality Q. Thus, there exists a field with Q elements. So this is interesting, right? Now, for the uniqueness, we have to do a little work. Let K and L be two fields with Q elements. We need to show that they are isomorphic. Now, since the unit group K cross of K has Q minus 1 elements, that is P to the power minus 1, by Lagrange's theorem, every element of A of k cross satisfies a to the power q minus 1 equals to 1. Therefore, a to the power q equals to a for all a belongs to k star. Since 0 of q equals to 0 as well, we have uh, a to the power q equals to a for all a belongs to k, and this means every element of k is a root of x to the power q minus x, and so x to the power q minus x splits completely into linear factors in kx, and similarly x to the power q minus x split completely into linear factors in lx. And now by the result mentioned in the problem, since k cross is cyclic of order q minus 1, there exists small x from k cross such that every element in k cross is a power of x, and that is that k equals to small k of x, where small k is contained in capital K, is the prime field of capital K. Now let mu equals to mu suffix x comma k of kx be the minimal polynomial of x over k. Then mu divides x to the power q minus x in kx, and since x is a 0 of x to the power q minus x, right, and as a divisor of x to the power q minus x, which splits into linear factors in L, the polynomial has a 0 of y(L). The substitution k algebra homomorphism epsilon y from kx to L, capital X going to small y, has mu uh, uh, contained in car of epsilon y. Therefore, car of epsilon y is kx mu, and epsilon y induces a k algebra homomorphism from capital K, which is small kx, which is this small kx by small kx mu to L. This is injective since k is a field. Since both k is a field, therefore it has trivial ideals only, and since this is a non-trivial map, so this is injective, and since both k and L have q elements, the injective map must be bijective, therefore they're isomorphic. So now we move into the last problem of today. So this is quite big problem, so please take some time to get familiar with this, and then we'll start doing this. Okay, so let us start with the last problem. So let F Q be the finite field with Q elements. and let capital F be a polynomial a0 plus a1x plus up to aq minus 2 of x to the power q minus 2, which is an element of fq of x with degree of f equals to q minus 2. Then the number of distinct zeros f of f in fq other than 0 is given by q minus 1 uh, minus rank of fq of f. So this is a famous formula, and this is very much used in number theory, where your small f is a field is a vector space map from fq to the power q minus 1 to fq to the power q minus 1, defined by the circular matrix, that is a0 a1 up to aq minus 2, a1 a2 up to a0, and aq minus 2 a0 up to aq minus 3, which is a matrix of order q minus 1 consisting of elements from fq. So we have to prove this. Now we consider the product, that is u dot b, where your u is this matrix, and uh, beta is this. So therefore uh, so uh, yeah, it's called the Van der Waals matrix, and of the non-zero elements of x0 x1 to xq minus 2. So how does this look like? It should be something like this. So it should be 0 x0, and this is 1 x 1 0. I mean, so it should be like this: x0 square 1 x1 square dot dot, something like this. Okay, and these elements should be 1 by the Fermat's little theorem. Now we first analyze the product u dot beta. The ijth entry of u dot b is u dot b ij, which is a summation of a to a of a suffix I minus k mod of q minus 1 x to the power k. So if you have any doubt regarding this, you can send me a mail. But this is fairly straightforward if you just write down to matrix and do out the product yourself. And if you simplify this, it should be something summation of this ak of x to the power k plus I by j. And again, doing this, it's if you carve out your x to the power I mean xj to the power I, should be summation k 0 to q minus 2 ak xj to the power k, and which is something like this: xj to the power I f of xj. Now the ith row of u is ai plus 1 aq minus 2 from a0 to a minus 1 with indices modulo q minus 1, and for the ith row, counting from I equals to 0, the entry in position k is ai plus k mod q minus 1, right? And if I recalculate it more precisely, the circular matrix has the form where the row I is a right shift of the row I minus 1, and so row 0, that is a0 upon q minus 2, goes to a1 a2 a3 up to q0. That means a0 goes here and these things goes up to here. So therefore the ith entry of u dot b is ai plus k mod q minus 1 to the power x to the power k, which I have written here. So now if we change the variables, that is l equals to I plus k mod q minus 1, then summation of ai plus k mod q minus 1 x to the power kj uh, equals to summation of uh, okay. So yeah, if you now simplify this term, you'll see that a to the power l xj to the power l minus y summation plus summation al xj to the power q minus 1 l plus l minus I should be equals to this. And from here we will see that x to the power minus I of j, I mean you are taking out this minus I from both side, and you will get this term. And this is xj to the power minus I f of xj into these correction terms. Now uh, for a circular matrix with first row c0 c1 to cn minus 1, the eigenvalues are lambda k equals to cl omega to the power kl, where l is running from l to n minus 1, where omega is the primitive nth root of unity. In our case, when n equals to q minus 1 and the elements x0 up to xq minus 2 form the multiplicative group fq cross, which is cyclic of order q minus 1. Thus, the elements have precisely the q minus 1th roots of unity in fq. Next, x0, x1 and xq minus 2 be the non-zero elements of fq. The Van der Monde matrix B has rank q minus 1 since all xj are distinct, right? And the product u dot b can be analyzed column by column. The jth column of u dot b is u dot b of j is of this form, that is xj to the power 0 fxj, xj to the power 1 fxj, and up to xj to the power q minus 2 fxj of to the power in the column form. And if you carve out your fxj, you get this. And if fxj is 0, then the jth column is 0 factor. If fxj is non-zero, then the uh, jth column is fxj times jth column of b, which is linearly independent from the other such columns. Therefore, rank of u dot b is number of j such that fxj not equals to 0, which equals to f of um, v of fq of f minus 0. And where the superscript c denotes the complement in the set x0 up to xq minus 2, which equals to fq cross. And since fq cross is q minus 1, we have vfqf minus 0 is q minus 1 minus rank of ub. By the rank nullity theorem and the properties of the matrix products, you know that rank of ub is the minimum of rank of u comma minimum of minimum of rank of u comma rank of b, which equals to minimum of rank of u comma q minus 1. And moreover, since b is invertible, we have rank of ub equals to rank of u. And this is because for any matrix and invertible matrix C, rank of bc equals to rank of b. Therefore, we have v of fqf minus 0 equals to q minus 1 minus rank of you. So you're done. So if you have any doubt, you can ask me in the email, or you can post it in the group. So we'll talk about later. And anyway, this lecture and the solution will be uploaded in the your conversation. So thank you.